Hello and welcome to Learning with Miss Doherty. All right, so last video I did was exponential functions without transformations, and this video is exponential functions with transformations, only a single parameter. And today we will discover what happens when one or more transformations occurs to the exponential parent function. We will need to have the function in general form, which is f of x equals a, which is the initial value, multiplied by the b, which is the base, raised to the exponential power of x minus c, plus d, where a, b, and c are parameters. We will explore each parameter separately to determine what each does to the parent graph. So we've got parameter A, parameter B, parameter C, and parameter D. Parameter is just a item that is going to have some kind of influence on our parent graph. Parameters can be time. So in other words, if you are working as an hourly employee, the parameters for you to not earn overtime is that you have to work 40 or less hours if you are in the United States. It just is a restriction of some sort or some kind of influence on the outcome. So parent function, that is our most basic function of our basic parent graph. So our parent function in this case is, since it's exponential, is that we will have f of x equals a. Well, actually, they will say that a is 1, and then times b, which would be whatever our base is, and our lowest base would be 2. So normally it's f of x equals base x, base raised to the x power. All right, transformation. Transformation means that the shape will be affected. Let's see. Okay, so in a transformation, the shape will be affected. Translation is the function moves. Function is moved without changing the shape. Okay. And the next video that follows after this is that we will have transformations and translations together. All right, symbolic form just means that it is in equation form. So that means our parent function that is in symbolic form is when we're going to have our output, f of x, is equivalent to our initial value times b raised to the x power. And so that is our symbolic form. Standard form. We also have our standard form in which something is, it's just generally written that way. So our standard form also in this case happens to be our parent function. So if it is f of x equals a times b raised to the x power. That's just our standard form. General form is we want to have all the parameters that we can do to a function. In other words, we can reflect it, we can stretch it, we can make it grow horizontally or vertically. We can shift it to the left, we can shift it to the right, we can shift it up, or we can shift it down. So in general form, we need four different parameters. So in general form, our function is going to be f of x equals a multiplied by b raised to the x minus c power plus d. Okay, two of these parameters will deal with the x and y axis, and the other two will deal with the stretching or compressing of the function across the x-axis or the y-axis. All right, changes to parameter a. So we're going to go through here and we're going to figure out what a does, what b does, what c does, and what d does. So we're going to start over here. I'm going to make it just a little bit bigger here so we can see over here on Desmos what happens to a. So we're going to put in our parent function first. And I'm just going to come over here. I'm going to go to f parentheses x. Now I won't have this where my touches and are going to show every single time on video, but I'm doing it this time so that you guys can see what I'm doing on Desmos. All right, we're going to have, again, we're going to start out with 1 parentheses, and we're going to start with the basic parent function of 2 close parentheses raised to the x power. That gives us a very basic base, a very easy base to see. So there's our first function, and we want to see what happens when we change that parameter a, which is out in front of the parentheses. We're going to what happens when we change our initial value, what happens to our parent function. So I need to come up with I could come up with a different letter. I could do g of x, or I could do f parentheses 1 of, let's do this, f2 of x, f2 of parentheses x. You just can't have 2 functions defined as f of x, because otherwise Desmos will say, hey, you can't do that. All right, so what occurs if I change that to, let's say, a positive 2? So we'll make that a positive 2, parentheses, 2, close parentheses, and we're going to raise it to the x power. Okay, well, I can see that I still have basically the same asymptote, that's y equals 0. I can see that I have a different y-intercept. It has went from 1, 0, or 0, 1 to 0, 2. And I can also see that it is growing just basically parallel to each other. That is, it's just growing and it's going faster. But what I need to do is I need to look at my two values in the table. So I'm going to pick this one. I'm going to grab its table. And I'm going to put into there its first function, which is just going to be f of x. F parentheses x. That way I can see what's going on with it. Okay, so I can compare these two, and I don't want I want these two to match. I want this color to match that one, so I'm going to make it red so it matches my first item there. Okay, so my original one, when I put in 0, I need to make that just a little bit bigger. When I put in 0, I got out 1, but this time I put in 0, I get out 2. In my original one, I put in 1, I got out 2. This time I got out 4. Last time I got a 2, I got out 4, I get 2, I got 8. See what happens when we put in 3. Okay, then 4. And then 5. Okay, so I can see whatever my output is, it's always going to be double what my original function was, which was my f of x. So I can see if my value is greater than 1, we can see that we have a vertical stretch. It's going to stretch more quickly. And I can also show that if I put in a third function. Let's do f of x. Let's see, f, and let's do 3 of x. 3 of parentheses x equals, what happens if I put in like a 5? Parentheses, 2, close parentheses, and I'm going to raise it to the x power. Okay, I don't want that to be red, I want it to be a different color, so let's do this one in green. Okay. And if I want to come over here and see what happens in my table, I can see that also this green function is growing much more quickly. It also will have the same, it will have the asymptote, it will have the same asymptote, but the different y-intercept is now crossing at the point 0, 5. Okay. If I come over here and add to its tables, let's see if this will do this. I don't know if it will or not. F3 of parentheses x, and it will. I want to put that in as green. Let's do this as green, because that's what I changed the color to. And I want to see what's going on with it now. All right, so when we put in 0, my original function, I got out 1. When we changed our a parameter to 2, it became 2. When we changed our a parameter to 5, it became 5. So I'm going to be looking at this one. 2, and it grew by a factor of 5. 4 multiplied by 5. 8 multiplied by a factor of 5. 16 multiplied by a factor of 5. So when I am dealing with a symbolic function like this, and they want to know what was my initial value, in other words, what is my y-intercept, I am going to look at that first. I'm going to look at what is out in front of that parentheses for the base. It's going to tell me what I started with. Okay, so anyway, oh, and that was just if it became greater than 1. So let's see what happens if it is less than, between 0 and 1. So let's see what happens if we put let's see, and let's do 4 in parentheses x. Oops, no, back that up. I need a parentheses first. And then we're going to make that equals, let's do 1/2 x. So 1 divided by 2, I need to arrow out to make sure I get out of that denominator, parentheses, and I want to put in 2, close parentheses, and we're going to raise it to the x power. Whoops, did not raise it to the x power. Raise it to the x power. Okay, I'm going to change its color. People say I say the color really weirdly, but I'm going to say orange. Okay, so now, remember our first function up here is in red, and I'm going to just kind of hide those for right now. I'm moving my green, and I can see that it is growing slower. It is slowing down. It's not growing as fast. So if I come up here and I put in f4 of parentheses x, close parentheses, I can see if I come over here to 1, we started out with 2, and then I come over here, it's 1, it's half. 4 and 2, it's half. We had 8, and it's coming out half as fast. It's growing half as fast as our first function. So we had 1 as our initial value, base was 2, and if we changed it to 1 as our initial value, and we change our base to 1/2, comparing that to our 1 with the base 2 raised to the x power, it's going to grow half as fast. Okay, so it's either going to do a vertical stretch or vertical compression, depending on if it is greater than 1, or if it is greater than 0 but less than 1, that's going to be a vertical compression. Okay, so we got those two. Go ahead and write that down. It affects the, let's put this over here, vertical stretch, a greater than 1, or compression, if it is between 0 and 1. Okay, so that is 2 of our scenarios that we have where our value is a positive number and it is greater than 1. It is a positive number and it is between 0 and 1. We cannot use 0 or 1 because otherwise we will not have stretcher growth. But then we have what happens if a happens to be a negative number. Now remember, we could not have the base be a negative number because we would have an oscillating function. So we're going to go ahead and do f of 5 here. F of 5, open parentheses, x, close parentheses. And we're going to do equals. We're just going to do a -2. Oh, well, let's just do a -1. So -1 parentheses. Our base is still 2, close, and we are going to raise it to the x power. Okay, and I really don't like black as a color, as a confirmation color. I want to make it purple, and I want that to be maybe like a 4. And I'm going to do that as a dashed line so we can see, compare the two. All right, go ahead and get that out of the way. All right, so we can basically see that it's following along the same asymptote. It has the same asymptote. We can look at our value of A, and that is going to tell us where it's going to cross our y-axis, because that's going to be our initial value of our function. But we can also see that it looks like it is just reflected. It is exactly the same thing that's going on. So in this one, our domain is going to be all real numbers. Our range in this case is going to be going from negative infinity up to 0. And then after that, it stops. So we would have parentheses, negative infinity, comma, 0, parentheses. Okay. Now, if we look at our two tables, I want to look now at this one right here. Come on. I want to look at, I'll go to its table, and I want to add to it f of x. So just f, parentheses, x, parentheses. I just want to see what's going on with those. And as you notice, it is the same exact values. It is just that they are reflected across the x-axis. And if you are dealing with the same thing, if we are changing our values of our function for our value of A, it will also change accordingly. So if I make this like a negative 1/2, it is going to grow twice as slow, so negative 1 divided by 2. And as you can see, it became, from our original function, it's not only being reflected across the x-axis, but it is now growing half as slow. So we normally would have gotten out a 2 on 1, got out a negative 1. So if we have a negative, it's going to be reflected across the x-axis, and then we see it still has those same characteristics as if our number was positive or negative. If it is a number between 0 and 1, it will be a compression. It's not going to grow as quickly. If it is greater than 1, so let's come over here and let's make this a 3. We're going to see that it's going to be reflected because we have a negative, but it's going to grow, it's going to be stretched 3 times as fast as our parent function over here, which is just our f of x. So as you can see, these are growing 3 times, but they are reflected across the x-axis. So parameter A has 2 jobs. It's over here, and it also and if A is less than 0, it reflects the function across the x-axis. Okay, that's what parameter A does. All right. We already know what parameter B does. Parameter B in the previous video, if B is greater than 1, it is going to be growth. We're going to have exponential growth, okay? If B is equal to 1, no growth. And if the value where we have 0 less than B less than 1, So if you notice we have the same thing that's mirrored here with our A, we will have exponential decay. We cannot be equal to 0, because otherwise we would have nothing, and B must be greater than 0 if B is less than 0. There is oscillation. Okay, so what it means is that, like for instance, if we had a -5 here, and if we have a positive number, we get a -5. However, if we get -5 raised to the second power, so we squared, you're going to get a +25. So we're going to have things that oscillate between negative, positive because of the exponents. So we cannot have it ever be a negative base. All right. And now we're going to come over here and see what happens when we have parameter C. What does parameter C do to a function? So I'm going to go ahead and just close some of these out. Change that back to a 1. Now, my original function here. Come on, be nice. And I want that to show up. It's going to just cover it up really quickly. And I'm going to make this just bigger. Now, parameter C, I'm going to come over here and I'm going to put it in parentheses here. If I do just subtraction, it's going to put me down on the baseline. So I need to come back over here, put this in parentheses, and I'm going to move this out here. And I'm going to do, let's say, subtract 1. And I'm going to close parentheses, and I'm going to delete this. Okay, so I have my two functions here. And as you can see, you would think, you can see that it's been shifted. It's been shifted over. And what I want to do is, I really wish I could take a screenshot of this. So I'm looking right here at this point right here where we have that, and then we're moving over here. So I want to look at that point, and I want to give me my point, put it in there. There we go. And we got our 0, 1. And I want to come over here to this one. Come on. You're not being very cooperative, are you? That one right there. It's going, nope, I don't want to be very, very cooperative right now. There we go. Come on. Okay, what if I put in 1, 1? Sometimes you have to do it's 1, 1. There we go. And I wanted to put that label on. So there I can see that it has shifted over from my y-intercept of 0, 1 to 1, 1. And so what it has done is that it has literally just taken that function. It has not stretched it or compressed it. It has not reflected it. It just took those values and shifted it over to the right one. So what I want to do is I'm going to put in my table here. This one. Put that table in. And I want to see what that other function is, f2 of x. So f2 of parentheses x, close parentheses, and I want to see exactly what is going on. So at 1, at 0, we had 1, and it shifted it over half. At 1, it was at 2, shifted it over to 1. At 2, it was at 4, shifted it over to 2. So as you can see, when we're looking at our table here, I have 0.25, and it shifted it down one step in my table. 0.5 shifted it down one step in my table. It was 1, shifted it down one step in the table. 2 shifted it down one step in the table. So if I put in 3, I'm going to get 8 for my f of x, and I should get 4 for my f2 of x. So if I put in 3, as you can see, it shifts it down one step in my table. So that just means that it's taking that value that we first evaluated when we had x, and we are taking 1 power away from it. So that's why it is shifting it down one step in the table. And how it looks on the graph is that it's going, okay, normally when I put in 2, I get out a 4 because that is 2 squared. But we had a 2, we took away 1, makes it actually 1, so it makes it a 2 in our table. So that's why it looks like that. So when we have it in standard form, we are able to see, hey, normally we are taking and subtracting 1 from it. It's going to move it 1 step down in our table. And sometimes you just go and put the function in, evaluate it, use the tables, and then graph it. But if I'm looking at it from the point of view of somebody who's graphing this, I'm going to say, hey, normally what I would do if this was me hand graphing this, it would be something like this. Come on, move. I am going to, actually, I'm going to say that shifts function to the right. Now we got to remember that this is a little bit strange. Normally most people are going to look at this. I'm going to just add another, no, so over here. I don't want this to interfere with everything else we're working with. All right, so we'll put over here just a little side work. So C is the thing that normally shows everybody off. We have, for our function, x minus c. This is subtraction. It is an operation. It is not that we are making that a negative c. We are really, if we wrote it out the way a mathematician would normally write it out, is that we would do x minus a positive c. Okay, so we are moving this direction 1 space. And you will often see when we are talking about the other direction, this is one I love Desmos, when we put in x minus a minus c, it will move it into the left direction. Now, a lot of calculators will make it x plus c. But you got to remember that we need this goes with our standard form, or our general form, that we need to have that subtraction, and to get it to be back to be a negative, it needs to be a negative c. Okay, so it's shifted to the right. Now I'm going to put it down that when C is positive. Not that the operation is positive. When C is positive, operation is subtraction. There's a fine line there, okay? So our operation is always going to be subtraction, and our C is positive if we write it that way. All right, so now let me come over here, and I'm going to change this one now so that instead of being a minus, subtract 1, I'm going to change it to minus 1. Okay, remember our original function? Our original function is in red, and now it shifted it here to over here. So now I have negative 1, 1. It shifted it to the left 1. So again, as I put it in Desmos, I left it as negative 1. I love how Desmos does that. Okay, take that one out. So I can also graph this as, I'm going to just do g of x this time, so I don't have to deal with this. G of x, I'm going to make the color green. Hopefully it'll come up green. All right, we're going to do equals, right now it's blue. Hopefully it will turn green when I get done here. 1 parentheses, 2, no, it's going to be red, but I'm going to change it. Raised to the parentheses, x plus 1, close parentheses, and again I'm going to change his color to green because I want to be green to show. All right, so as you can see, go ahead and take that out real quick. As you can see, we have the same function. If I take that off, it becomes blue, green. Take the blue one off, green, that goes away. They are interchangeable. If I bring up my two tables, so I'm going to just bring up here, there's f2 of x, I'm going to bring up g of x. Okay, come here. I'm going to add in another table here. Oh, I'm going to add one more here. Come on. Oh, okay, if you ever do anything like that with Desmos, you can just hit undo. Okay, come on. I want you just a little bit wider here. Thank you. So now I can come over here and type in g of x. So that we can see that those are both equivalent. I can see that f2 of x and g of x, the one that has it as the operation is addition, and then the one that has it as that I'm going to change my color so they actually match. That's blue, and I want this one to be green. Okay. So that I can see that my blue and the green, this is the way f2 of x is how most mathematicians would prefer it, because we want that operation and showing that it is going to be subtracting a negative one from whatever our exponent is. Okay, instead of having to sit there and unpack, hey, I'm supposed to have an operation of subtraction, and how do I get an operation of subtraction? Well, I've actually got to be going in the opposite direction. So shift the function to the left. Shifts. Come on, let's move this out of the way here. To the left. When C is less than 0 or negative. Okay. And operation is subtraction. If it is x plus c, change to x minus c. Okay, that's what you need to do when you do that. Okay, it's going to shift it left, it's going to shift it right. Make sure that you have that operation. This is the operation right here. The operation needs to be subtraction. I cannot stress that enough. Okay, all right, our next parameter is d. Let's go ahead and just delete some of these here. I'm going to go ahead and take that out. All right, so if I have f2 of x, f2 of parentheses x, and I'm going to go equals 1 parentheses 2 parentheses raised to the power of x. I'm going to error out of that, and I'm going to do plus, let's do 2, actually let's do 3. All right. Write that down. And as we can see, we have both functions are growing. We have a different asymptote this time. Our domain is going to be the same. Our range, however, our range is going to be that our asymptote is going to be approaching 3 instead of 0. because it's been shifted up 3 units. Normally we start here at 0, 1, and now we are at 0, 4. It's been shifted up 3 units. So if D shifts it up 3 units when we add 3 to it, what do you think is going to happen if we make it a negative 3? So let's find out. What happens if I do F3 of parentheses X equals 1 parentheses 2, not 5, back up, I want 2, close parentheses. I'm going to raise it to the x power, get out of like that, and I'm going to subtract 3. All right. Oh, didn't need to do that. It looks weird. Close that down. And as we can see, it's now 0, negative 2. So we have to remember, where does our parent function usually cross our y-axis? Is our y-intercept is 0, 1. If we are shifting it down 3, instead of crossing at 0, 1, it will cross at 0, negative 2. And our asymptote should be approaching a negative 3 instead of a positive 3. So let's go ahead and look at those 2 tables. Actually, those 3 tables. Let's go here. I'm going to grab this one. I'm going to put in f2 of x. F2 parentheses x. Oh, no, I did that wrong. Can you get my parentheses around the x? Okay. Take x and take that x out. And that one was in blue. I do want to match it. Thank you. All right. And I want to do f3 of x. F. Parentheses x, parentheses. Okay. Now I want some more negative numbers to see what my asymptotes are going to be approaching. So, negative 3. 4, negative 5, negative 6, negative, oh, not negative 6 again. How about negative 7? Not 76. How about negative 7? Oh, how about that one? Negative, let's do 20. Okay, as we can see, well, maybe even 25. We can see as my numbers become more and more negative, that my f2 of x just approaches 3. It says I'm going to approach 3. I'm never going to get past 3. Let's put in negative 26. So there just gets to be a point where it says, okay, no, we're not going to get any greater than this. We're not going to get any smaller than this. It's not going to be any less than this. I can put in negative 100, and I'm going to get 3 for my f2 of x and negative 3 for my f3 of x. So let's put in negative 100. Again, I get 3 and negative 3. I can put in negative 1 million. I don't know how I have. Yeah, that's 1 million. I still get, okay, eventually I get to where that's going to say 3, and then the other one should say like negative 3. If I arrow over here, let's come on tab. It's not going to let me see over there. Nope. I'll just go ahead and close this one out. So I can see that it even goes to negative 3 down here. So D is going to shift it up and down. So when, oops, and when D is greater than 0, it's going to shift it up D units. And similarly, when D is less than 0, so it's a negative number, it will shift it down D units. Okay. All right. So again, most of the things are not affected if it is a change in parameter to A, if the A is positive. There is not a change in like our main characteristics. If our B is changed, it just changes what our end behaviors are. So our domain and our range remain the same. Domain and range remain the same if A is just stretched or compressed, but not reflected. When it's reflected, it does affect the range. It does not affect the asymptote. It does not affect the it does affect the y-intercept, and it does affect the range. But otherwise, it does not affect much. I mean, there is some changes to the end behaviors, but domain remains the same. Our asymptote remains the same. Let's see. C will change, not the asymptote. It doesn't change the asymptote. It just shifts it left or right. So it will change the y-intercept based off of the shift. So you have to think about that. But it does not change our end behaviors. It does not change our domain. It does not change, well, it does not change the range either, because it's just shifting it left or right, and it will change the y-intercept. Okay. D will change our asymptotes. It will change our y-intercepts. Okay. So you have to think about all those things when we're looking at that. Parameter is just a restriction. That affects the graph. Okay, so again, our parameters, A can only change vertical stretch and compression. It cannot affect whether it's shifted up or down. Each parameter has its own restriction and what it can do to the parent graph. All right, so we've already went through and did what we did to our changes parameter A, B, and C, and D. And so we will be putting together in the next video what occurs if we have two or more translations and transformations. What happens if we put all four of them together? What happens if we put where we have reflected A and compressed A? Or what happens when we have stretched A and reflected it? How do we know when we're looking at it symbolically? So anyway, that is the next video. And again, thank you for coming to learn with Miss Dory.